Okay, so we of course love to solve equations. We're mathematicians, right? We're scientists. We love to solve equations. And there are some differential equations that can be solved. One class of differential equations where we usually can solve the differential equation in explicit form is a separable equation. So up to now, differentiable equations, you've been studying them and doing different things with them. But now we're actually going to solve a differential equation. Right? So what we want to do is we want to solve the initial value problem given by the differential equation y prime equals x squared over y squared with the initial condition y of 0 equals 2. Okay, so this is what's called a separable equation. Right. So let me ask you, the derivative. Well, what are the variables in this equation? What are our variables? This differential equation, well, it has two variables, right? The x variable and the y variable. All right. And what we want to do is separate the differential equation so that x variables are on one side and y variables are on the other side. So let me show you how this would work. Okay, so I want to move to the solution here. All right, so first of all, I'm going to express y prime as dy dx. Okay. I'm expressing y prime as dy dx. Y prime is a derivative is a rate. And the rate is a fraction, right? I mean, a rate is dy dx is a fraction. I mean, well, hold on here. dy, when you, in calculus 1, when you were first introduced to the derivative, whoops, hold on, that's not right. So dy dx is the slope, and the slope is the change in y over the change in x, right? How many have seen this from calculus 1? That and of course, if we let delta x approach 0, these will be equal. But how many have seen like delta y over delta x in related to before you like in relation to the derivative? Maybe in calculus 1. Good. Thank you, Josiah. Thank you, John. So you know, so dy dx, we can treat it really, thank you, Raymond, we can really treat it like a fraction. Since for when delta x is very small, the ratio of delta y over delta x, is equal to dy dx. Delta y over delta x would actually be the slope of a secant line. Okay, and the secant lines, as you let delta x get smaller, the secant lines, the slopes will approach the slope of a tangent line. But basically, then for delta x very small, for delta x small, for delta x small delta x, this, for small delta x, this fraction here, this fraction is essentially equal to the derivative, dy dx. So we can treat dy dx like a fraction. And what we're going to do is we're going to multiply both sides of the differential equation by y squared. The reason I want to do that is, and we'll get to this in a minute, but I want the right side of this differential equation to only involve x variables, and the left side of the differential equation to only involve y variables. So that's why I multiply by y squared both sides. And incidentally, we're assuming that, just so you know, we're assuming that y squared can't equal 0, right? Or I should say, because of that, y of course can equal 0, right? Because if dy dx is equal to x squared over y squared, y can't equal to 0. So okay, now we have y squared dy dx equals x squared. All right, and what I'm going to do now is I'm going to multiply both sides by dx. Hold on here, I'm going a little bit ahead of myself. I'm multiplying both sides by dx. By virtue of the fact that for this differential is approximately equal to delta x when delta x is small. So I can treat that like delta x. When I do that, why would I do that? Because by doing that, I remove the dx on the left side, and I have y squared dy equals x squared dx. So I've rewritten this differential equation in this way by the procedure called separating the variables. Separating the variables. Are there any questions so far? Okay, all right. So now we have an equation here, and what we do to the left side, we have to do to the right side. So I'm going to choose to integrate the left side of the differential equation, but then I also must integrate the right side of the differential equation. And our goal, remember, our goal is to solve for y. We want to find the solution to the differential equation. The goal is to solve for y. Well, okay. Are there any steps on this part here? Are we okay with that? Okay, well now we're going to integrate both sides. The antiderivative of y squared is y cubed over 3. Similarly, the antiderivative of x squared is x cubed over 3. But remember, these are indefinite integrals, so we have to have constants of integration on the left and right side. And they don't need to be the same either, right? I have a C1 on the left side and a C2 on the right side. Now remember the goal. The goal is to solve for y. So what I'm going to do is I want to isolate the y. I want a y on the left side. I don't want y cubed over 3 plus c1. So first thing I'm going to do is subtract the c1. I'm going to subtract c1 from both sides. Right? It's an equation. And when I subtract c1 from both sides, I'll get y cubed over 3 equals x cubed over 3 plus c2 minus c1. But what is c2 minus c1? c2 minus c1 is just another constant. Okay, it's just another constant. This work is important to show. It is important to show. It's necessary to show. And you know, I look at the work, I look at your process when I grade your exam work. It would be okay to go from this step to this step if you wanted. In other words, this intermediate step here where I have a plus C1 on the left side and a plus C2 on the right side, well, you know, and that's going to occur all the time, right? Because this process works the same for all the problems. So you could go from, let me just phrase it the way I want to phrase it. You could go from this step here down to this step, where you have y cubed over 3 equals x cubed over 3 plus c3. You know, that would be okay, because if you do that, I understand then that you know that you're just rearranging, you're just doing this process here. Okay, all right. So now we, you know, again, we want to solve for y. And it looks promising, right? It looks promising. This is just a little equation here that we need to solve. So if I go to the next page, and everybody's good so far? Okay. If we go to the next page, we have y cubed over 3 equals x cubed over 3 plus that constant. What I'm going to do now, well, how do I get from this step to this step? What did I do to the equation to go from this first step to the second step? Who can chat it out what I did? That's right, Marvis. I multiplied by 3 on both sides of the equation. Okay, I multiplied by 3 here, and I multiplied by 3 there. And by doing so, I get y cubed equals x cubed plus 3 times c3. Okay, and now at this stage, I'm pretty close to solving for y. I don't think I'll be needing to alter the constant anymore, so I'll write c3 as big K, or you could write as big C. But you do need to have the constant change. Okay, in other words, if you were to write y cubed equals x cubed, you know, after multiplying by 3 both sides of the equation, if you were to write y cubed equals x cubed plus c3 and didn't change that constant, that would be wrong. Because you don't have c3 anymore. You have 3 times c3. And that's a new constant. So this is very important to track your constants as you work through the problem. And sometimes you're going to, you'll go from C1 constant to C2 constant to C3 constant to, constants they'll change sometimes 3 or 4 times as you do the algebra in the problem. Okay, so y cubed equals x cubed plus k. To isolate the y, we take the cube root of both sides, right? We take the cube root of the left side, and we take the cube root of the right side. Okay. All right, let me just write that again. Take the cube root of the left side. And the cube root of the right side. And you'll get y equals the cube root of x cubed plus k. And that's a family of solutions. You have a family of solutions here. It's the general solution. And again, we could plot that family of solutions on our calculator by just changing the value of k and graphing, 6 or 7 functions. We'd get a feel for what the family looks like. And I'll actually show you a figure of the family. But remember the question. The original question was to solve the initial value problem. Well, when x is 0, y equals 2. So when we add that condition to our solution, we're going to get a unique solution. We're going to be able to solve for k. So if y of 0 equals 2, 2 will equal the cube root of 0 cubed plus k. Hence, we get 2 equals the cube root of k. And that means k equals 8. K equals 8. Are there any questions on that problem? Any questions so far? Okay. Well, then the solution to this IVP, what do you think that symbol, what do you think the letters IVP stand for? MVP is most valuable player, right? But we don't have that here in our differential equations. That's right, Robin. IVP stands for initial value problem. So the solution to our initial value problem is y equals the cube root of x cubed plus 8. And in the picture here, in the figure, and I pulled this figure from the book, Figure 1 shows graphs of several members of the family of solutions of the differential equation. The solution of the initial value problem in part B. So what I've done was example 1, the solution to the initial value problem is shown in red. However, on the scan, the red didn't come out. So is there anybody who would like to You're able to. We're able to share the whiteboard. I remember I have that as a participation. That's why the anonymous student yesterday was able to write on the picture there that I had. So can anybody take the pen? You all should be able. I think you all should be able to do this. I assume the Blackboard Collaborate will, the first person that decides to do it it'll let them do it. I want you to, so how many solutions did they draw here, by the way, in this family of solutions? How many solutions are drawn? Just out of curiosity. And I'm talking the curvy solutions, How many solutions do you see? Well, Josiah, there are 3 here, but what about over here? 6 solutions, 6 curvy solutions. And I would like one of you to shade in red to trace out the solution that where y of 0 equals 2. So it's got to be one of the 6. I can trace out the solution, but I want to see if anybody here can take the pen and trace out the solution. If you can't, I can make you a presenter, and then you'd be able to do it. So would anybody like to try this, to use the pen? Do we have any volunteers? Raise your hand if you're interested. We want to trace out the solution that passes through the, well, put it this way. This is our solution, right, that we want. Y equals the cube root of x cubed plus 8. That's the solution to the differential equation that passes through 0, 2. So I'm going to give you another 20 seconds to see if anybody wants to trace out the solution. And then if you don't want to do it, that's fine. I can trace it for you. Is anybody afraid of tracing the wrong curve? Oh, wait. Okay. All right. Wonderful. Excellent. Thank you. Who, if I may ask, who did that? You can stay anonymous if you want. So great. Well, see. Okay. Thank you, Robin. Very good. There you go. All right. Are there any questions on this? Any questions? We'll be doing more separation of variable problems tomorrow. We'll be doing some word problems, some applications. Okay, but what I'd like to do for the last 10 minutes of class, and please, as always, if you could stay in the class session, I'd appreciate it. But I've activated the section 7.3 exercises in WebAssign. And I'm just removing the restriction on it. And why don't we, okay, let me remove the restriction. And actually, let me stop the recording here.